Okay, so this is going to be the section on critical numbers. So you can access these notes on Canvas on the 12.3 notes. Okay, so to talk about, before we start talking about critical numbers, let's first start talking about differentiability. So we've talked about curves and functions that have different shapes and figures, right? Some of them are more curvy, some of them have little corners. And the ones that we've really been working with is a lot like this one. So the first one. And what we've been talking about for the previous past couple of weeks has been derivatives. So we've been talking extensively about derivatives. And really, when we have some sort of graph that's maybe not given to us explicitly, so we don't have like f of x equals x cubed minus 2x squared, something like that. So if we don't have that explicit, we can still talk about derivatives in a graphical sense. What we're going to do here is we are going to look at what can be differentiable and what cannot be differentiable. And this is more in the graphical sense. So if you kind of look at any point in this first graph, you can see that the slope is defined everywhere. So remember, the slope is just the slope, or the derivative, is just kind of like, imagine that you have a tangent line on a particular point, and that tangent line is going to give us a slope. And you can see that at every particular point, you're always going to have a slope. The slope is going to be defined. Okay, you can see that in the beginning at point 1, you're going to get like a positive slope. Then when you get to the very peak, you're going to get a 0 slope. When you get to the bottom at this point P2, you're going to get a negative slope, then 0, and then a positive slope again. So it's kind of changing all throughout. So here, this function, we will call it differentiable, because you can take the derivative everywhere. At every particular point, everything's going to be defined. Okay. Now, graph number 2 is a little different because, and this is kind of like what we were talking about as a challenge problem in our past exam. You can see that if I were to choose any point here, you're going to get a slope, and the slope is constant here. It looks like it's going to be like about a negative 1 because it's going downward. See how it's going downward? The slope is negative. And then after 0 is going to be positive. Okay, but you can see here that at the point x equals 0, well, that's going to be a little hard for us to kind of figure out, because you can see that the slope here is undefined. So we got an undefined slope. So here is this particular graph, which is the absolute value of x, is differentiable. So you can still take the derivative of it, except at x equals 0. So at x equals 0, this guy is, you cannot take the derivative of it. Okay, and in any particular case, corners, so any graph that has a corner, the graph itself will not be differentiable. So if the graph has a corner, this is the equivalent to saying not differentiable. So you will not be able to take the derivative there. Okay. Now we have these next 3 graphs. Again, you have a corner here. You can see you got a corner. And then you also have another corner. Again, these 2 graphs will be differentiable everywhere except at those particular corners. So this guy will be differentiable everywhere except at the point C. Okay. And then for this one, this 4th graph, this guy will not be differentiable at x equals c, because now you have a vertical tangent. So if you remember taking a line tangent to that, you can see that at this point, the graph tangent to that will be vertical. So this guy will also not be differentiable at x equals c. So not differentiable at x equals c. So it's differentiable everywhere. Everywhere else you can take the derivative, you can plug it in, but except at x equals c. And now this guy, number 5, we do have corners, but usually whenever we have something that looks like that, and when we start graphing some of these problems, we'll get something that kind of looks like this, like kind of like angel wings. These are usually what we call cusps. So something like this is what we call a cusp. You can see that you got like little cusps there. Okay, you can also call them corners. And in that point, this one will also be not differentiable at these particular points, so not differentiable at x equals -2, x equals 0, x equals 2. So they won't be differentiable anywhere there. Okay, so we want to kind of have a little bit of an idea of things that are differentiable and not differentiable. Okay, so why was this important? So this is going to be really helpful when we start thinking about critical points. And critical points is just a point in the graph in which you have a horizontal tangent. So that's the first thing. You're either going to have a horizontal tangent or you're going to have an undefined slope. Okay, so you can see that whenever we find a critical point, they will appear whenever you have a horizontal tangent. So if we go back up and we see where exactly were the tangent lines horizontal, well, you can see that the tangent lines were horizontal here and here. Okay, so you see that the tangent line at those particular points were horizontal. So it's basically at the bump. So if you think about this as a mountain, it's like at the highest point and at the lowest point. Okay, so that's where the graph has a horizontal tangent and it's undefined. Well, when is it going to be undefined? Okay, well, you see that it's going to be undefined somewhere here, right? Also the corners, there's not differentiable there. At cusps, at vertical tangents, all of those guys are undefined. So that's what critical points are. So if I can find all of these points where all of these guys exist, where you have little bumps, horizontal tangents, and when you have corners, cusps, and even this, we will be calling them critical points. So the way that you kind of find a critical point, it's pretty straightforward. You just take the derivative and set it equal to 0. And that kind of makes sense, right? Because if you have a graph, then the horizontal line is going to be wherever the slope is 0. We know the slope is the derivative, so taking the derivative and setting it equal to 0 is basically what we want to do. And now, one thing that we can also do to find where everything is undefined is after we take the derivative, just look at all the points where it's going to be undefined. This guy is going to give us all of the points, okay, where this guy is going to be undefined. So something like that, for example. All right, so this are just all the corners. So that's how you find critical points. So there's two different steps, well, kind of two different steps. So it'll make sense when we do a couple of problems. So here we want to have, I have this important note. So a critical point must exist in the domain of f of x. So whatever point I find, they have to be in the domain. Okay, and what that means is that when I plug in that x value that I find here, and I have to plug it back into the original, I can't get something that's undefined. Okay, I have to make sure that that it is within the domain. So that's a common misconception. Usually when that happens, what you really have is asymptotes. So for today, you don't have to worry so much about when it's not in the domain. We'll do that some other time when we start graphing rationals with where things are not within the domain. Right now, we're only going to worry about these two different criteria. Okay, so one more note is that critical points can be classified as minimums, maximums, or neithers. Okay, so how can that possibly be? Well, if you find a critical point and you want to know whether something would be a maximum, well, this is a parabola. You can see that the slope is going to be 0 here. You can see that here, this critical point will be considered to be a maximum. So at x equals, I don't know, 3, it will be a maximum. Okay, so the critical point will be x equals 3, and then this will be my maximum, whatever the y value may be. When would it be a minimum? Well, kind of like the opposite. You can see that the horizontal tangent line is still going to be 0 here. Maybe this is x equals 3. And now we arrived at a minimum. So we can have something that looks like that. So when will it be neither? Well, that means that it's neither a maximum or a minimum. So that means that from here to here, it looks like you have a maximum, right? You can see, oh, I'm going to get a maximum. But instead, it turns around and it becomes a minimum. So you can see that if I were to take the path of this part, you can see it kind of looks like a minimum from here to here. If I just look at from x equals 0 to forward, it kind of looks like a minimum. But if I take it from x equals 0 and then backward, you can see that it kind of looks like a maximum. So this point right here is neither a maximum or a minimum. And usually we call it a saddle point. So these are what we call saddles. Okay, so that's what we have there. So this would be a really good example of what maximums, minimums, or neither would look like. And obviously a maximum and a minimum can also have a corner. If you look back at the absolute value, you see that even though we had something that was not differentiable, the derivative was undefined here, then even though we had that, we still have a maximum or a minimum. So you have to not only look at just the horizontal tangents, you also have to look at wherever it's undefined. Okay, so let's do a couple of examples, and I have a ton of examples here for you to do. So we want to find the critical points. So remember, in order for me to find the critical points, I need to do two different things. I need to take the derivative and set it equal to 0 and solve. And, well, I also have to do this also. I have to see where exactly is the derivative undefined. So there's two things that I got to take care of. For the most part, we're going to be doing number 1, and I'll show you when we can do number 2. So let's do the first problem. We have this function, f of x equals x cubed minus 12x squared minus 60x plus 30. We want to find all the critical points. Now, obviously, we could easily just graph this and just identify, oh, here it is. But we just want to do it algebraically. We want to be able to use calculus. So the first thing that we're going to do, we're going to take the derivative of this. And taking the derivative of this will give me 3x squared minus 24x minus 60. And now that I take the derivative, I'm going to set this guy equal to 0. Okay, and now what I'm going to do is now I have a quadratic equation, 3x squared minus 24x minus 60 is equal to 0. So I got that. So one of the things that I can do, I now have to use my algebra knowledge to be able to solve this. So this is a quadratic. You can use quadratic formula or you can just factor. So I'm going to take out a 3 first, and I'm going to have x squared minus 8x minus 20 is equal to 0. All right, so I can divide out the 3. The 3 doesn't really do anything here. Divide out this 3, so you got x squared minus 8x minus 20 is equal to 0. Okay, and now we can just factor this guy out. So you can see that if this is 10 and 2, then I can just make this guy be negative and this guy be positive. So what I end up getting is x equals 10 and x equals negative 2 as my critical points. So these guys would be my critical points. So right now we just want to find the x values. Later on we'll find its respective y values. So what we just found is that if I were to have a graph, okay, of this guy, if I were to graph f of x, then at x equals 2 and at x equals, negative 2. At x equals negative 2 and at x equals 10, I would have some potential maximums and minimums. So maybe the graph kind of looks like this. I'm not sure. Maybe the graph goes like that, and then maybe it goes like that. I don't know. I don't know what this graph looks like. I'm just making this up. But this is kind of what it's saying. At this point, you have a horizontal tangent, and at this point, you have another horizontal tangent. Okay, that's what this is saying. Okay, so I was able to find the bumps of this particular graph. That's what I just did. Now later on, I'll show you how to actually graph this guy. But right now we just want to find the critical points. Now, do we need to check if it's undefined? Not really, because you can see that once we took the derivative of this guy, there's nothing undefined. We don't have any x's on the bottom. We don't have anything that we need to really, that makes this is a polynomial, right? Nothing is going to be undefined at this point. So this is just going to be it. All right, let's do this next problem. So we got y equals this guy. So we want to find the critical points. So let's start off by taking the derivative first. So this is going to be 4x cubed minus 12x squared minus 16x. The derivative of 64 is just 0. And then we're just going to set this guy equal to 0. So notice here, now we have a cubic, right? Graphing cubics are a little harder, but notice that I have an x on every single term. So I also can factor out a 4, and I'm going to factor out an x. So I'm going to have x squared minus 3x minus 4 is equal to 0. And then you can see that we can factor out this guy right there. So we're going to have 4x, and then factor this guy. So you'll have x and x. You'll have a 4 and a 1. And then this guy is going to be minus, this guy is going to be plus. So we're going to set all these three different factors equal to 0. So 4x equals 0, x minus 4 is equal to 0, x plus 1 is equal to 0. So you're going to get x equals 0, you're going to get x equals 4, you're going to get x equals negative 1. So those guys are going to be my critical points. So this guy is where I can get a maximum or a minimum, or they can be nothing. Okay, so it really just depends. Okay, so these guys can give me maximums and they can give me minimums. Okay, that's basically the whole purpose of this. I can acquire maximums and minimums by taking the derivative and setting it equal to 0. Okay. All right, so far we haven't dealt with anything that's undefined. Everything has been just very straightforward. Because again, if I take the derivative of this guy, you can see that all of this is a polynomial. The polynomials have a domain of all real numbers. Now we're going to deal with things that maybe are not differentiable everywhere. So let's start off with this guy. So remember, we're going to take the derivative first. So f prime of x is going to be equal to, so I'm going to take the derivative of this guy. So I'm going to move this forward and subtract by 1. So 18 times 1/3, that's going to give me 6x. And then I'm going to have 1/3 minus 1, which is 3 over 3. That's going to be negative 2/3. And I'm going to set this guy equal to 0. Okay. And now let me rewrite this a little better. So let me move the x to the 2/3 on the bottom. Okay. All right, and now let me solve first. Okay, so let me go ahead and solve it. So notice that I can move the x to the 2/3 to the other side. Oh, but what happens when I do that? So if I do that, I'm just going to get 6 is equal to, well, 0 times x to the 2/3 is just 0. Oh, I don't have anything. That means there's no solution here. So no critical points for this guy. Okay, so I'm left with nothing. Okay, now notice here that this doesn't mean that there's no critical points. I mean, still, you can still get a critical point, but we need to now check the second part. So because this was the first part, we just set the derivative equal to 0. The second thing that we want to do is we want to check when is the derivative undefined. Is that even possible? So let's see. So right now we know that the derivative is 6x to the negative 2/3. Well, if I change this up a little bit, I get 6 over x to the 2/3. When can this be undefined? Well, this is just a rational equation, right? So I know that this bottom part cannot be 0. So x to the 2/3 cannot be equal to 0. So the only point, so if I were to kind of get rid of this guy, so to get rid of this guy of x to the 2/3, you can just write it a little bit differently. You can write it as x squared and then have it as a cubed root. Okay, you can just rewrite it as a radical. I can take the cube to both sides. X squared, oops. So you got x squared is equal to 0 or not equal to 0. And then you can just take the square root to both sides. And notice that it still get x equals 0. Or x cannot be equal to 0. So that means x cannot be equal to 0 on the bottom. And that was kind of obvious in the beginning. But later on, there might be some problems where it might not be obvious, where you actually have to solve this problem. So in this case, x is equal to 0 is not going to be a solution for this guy. So that means my only critical point is going to be wherever this guy was undefined. Where was this function undefined? At x equals 0. So x equals 0 is going to be the only critical point that I have. I know I cannot plug in x equals 0 in here. I can't plug it in into this derivative, but that's what I wanted. I wanted to see where exactly this is undefined. Okay. Obviously, you can plug it back into the original equation. You can see that it's within the domain. If I plug in 0 into the original, it is within the domain, so it's not an asymptote. Okay, so let's do this next example. So something a little bit more weird. So let's start off by taking the derivative of this, because we still want to find the critical points. So I want to take the derivative f prime of x is equal to, this is going to be 1/3 x, and I'm going to subtract the 1. That's going to be 2 over 2, so that's going to be negative 1/3. I'm going to move the negative 2/3 over. That's going to give me a positive 2/3 x to the power of, I'm going to subtract the 1, so that's going to be negative 3 over 3. It's going to give me negative 5 over 3. Okay? Should be a 2. Right? Because minus 3 over 3, that's going to be negative 2 over 3. Okay, perfect. Okay, so now that I got that, now I got to think about what I'm going to do with this. So I'm going to set this equal to 0. And now I have to think, okay, how can I practically solve something that looks like this? And here, think about like having x squared minus x equals 0. Well, one of the things that you do is you pull out the smallest number. So you can see that the smallest number between 2 and 1 is just 1. So I'm going to pull out 1x, and I just left with x minus 1. So similarly, I can also have x cubed minus x squared minus x to the 4th equals 0. What would be the smallest exponent? Well, in this case, it's x squared. So I will pull out x squared, and I will just be left with x minus 1 minus x to the second power. Okay, so that's what you would have at the end. So you're going to do exactly the same thing here. In this case, negative 5 over 3 would be the smallest number. So we are going to factor out an x to the negative 5/3. And remember, whenever we think about factoring out, we're thinking kind of like of dividing. So think about how I'm dividing a negative 5/3, or an x to the negative 5/3. So think about it that way. So that means here on the second term, I don't have anything left other than just a 2/3. Here I have a 1/3. And if I divide an x to the negative 2/3 divided by x to the negative 5/3, well, remember when we have exponents, we're just going to subtract the exponents. The negative 2/3 subtracted by negative 5/3. And if I just look at that, you're just going to get 3 over 3, which just gives me 1. So I'm left with one single x. Okay? If you need to rewind the video again, just do it. Okay? Because I know this can be a little confusing. And then we're just going to set this guy equal to 0. Okay? All right, and now all I really have to do is just set both of them equal to 0. So I got x to the negative 5/3 is equal to 0. And then 1/3 x plus 2/3 is equal to 0. Okay? All right, and now what I have to do is that I have to solve for this guy. Well, this guy, 1 over x to the 5/3, I can write it a little better. Notice that for this guy, if I move that other guy over, so the x to the 5/3, I move this guy over, this is going to go away, and I'm left with 1 equals 0. So I got nothing there. And then for the other one, I'm just going to solve this equation. Subtract by 2/3 to both sides. So I'm left with 1/3 x is equal to negative 2/3. I'm going to multiply both sides by 3. And then what I'm going to get is just x is equal to negative 2. So that's going to be my answer for that guy. And remember that this is just the first step. That's just going to be the first particular problem for setting the derivative equal to 0. Because now what I got to do is where exactly is it undefined? And for it to be undefined, well, let's look at the undefined term. So I know f prime was equal to, well, when I factored everything out, I ended up getting x to the negative 5/3, 1/3 x plus 2/3. So you can see that the only thing that's kind of undefined here is this guy. This guy's the only one that's going to give me an undefined term, because if I write it a little better, 1 over x to the 5/3, 1/3 x plus 2/3, you can see that this guy cannot be equal to 0. So x to the 5/3 cannot be equal to 0. And you can kind of see that it's kind of obvious that x equals 0 is going to be one of the points where that cannot be it. So you have two critical points here. So x equals -2 and x equals 0. All right, let's do another problem. A few more. So let's see this one. So here now we have a multiplication of two different things. So here we're going to have to do the product rule because there's two different multiplications, this guy and this guy. So I'm going to take the derivative of this. Remember that this is just t to the 2/3. So I'm going to go ahead and take the derivative. So it's going to be 2/3 t. I'm going to subtract by 1. So that's going to be 3 over 3, gives me -1/3. Then I'm going to leave the next one by itself. Plus, now I'm going to take the derivative of the second one, which is going to be 2. And I'm going to leave the next one by itself, t to the 2/3. Okay. So now what I have is just 2/3 t to the -1/3, 2t minus 1, plus 2 t to the 2/3. And I'm going to set this guy equal to 0. So now what you can see is that I'm going to look at the same thing. Notice that this guy and this guy have common factors. So I'm going to factor out the lowest exponent. In this case, will be the -1/3. So I'm going to pull it out. T to the -1/3. Pull that guy out. And what's left over is this 2/3. I still have that 2t minus 1 sitting there. And then I have a 2 there. So notice that since I pulled out that t to the -1/3, I have nothing in the first one. Here I'm going to divide out a 2t to the -1/3. So imagine that I'm like dividing out a t to the -1/3. So I'm subtracting these two guys out. So you have 2/3 minus a -1/3. And you're just going to get a 1. So I'm left with just t, 1t. Setting it equal to 0. So I have, this guy's going to be 1 over t to the 1/3. Here I can FOIL this guy out. So I'm going to get 4/3 t minus 2/3 plus 2t equals 0. And I'm still going to get 1 over t to the 1/3. And then I can combine the 4/3 with the 2. That's going to give me 10 over 3. T minus 2/3 equals 0. And now we're just going to set this guy equal to 0. You're going to have 1 over t to the 1/3 equals 0. And then 10t over 3 minus 2/3 is equal to 0. So this one, you can easily see that this is going to give me nothing. Okay, nothing's going to happen there. Just like how we did in the previous problems. And now I'm going to add the 2/3 over. Oops, that should be a 3. And then I'm going to multiply both sides by the reciprocal, 3 over 10. So you're going to get that t is equal to 1/5. So that was the only critical point that I got by taking the derivative of it. And now what I have to do is I have to check when exactly is the derivative undefined. And the derivative is going to be undefined. So if we look at where exactly we stopped, this is the most condensed that we got with the derivative. 10 over 3t minus 2/3. You can see that this guy is the one that's going to give me an undefined term. So t equals 0 will also be a critical point, because that's where you're going to get an undefined term. Okay. All right, so we're almost done. We're going to do a couple more problems. We have 3 left. So now let's deal with some trig functions, because you can also do it with trig functions. So we're going to take the derivative of this guy. So the derivative of sine of x is just going to be cosine of x. The derivative of 1 is just going to be 0, and we're going to set this guy equal to 0. So now what we have to look at is where exactly is the cosine equal to 0. So we got to think about the unit circle. And we've got to think about all the points in which cosine is equal to 0. And you can see that the cosine itself, which is the x value on the unit circle, is going to be equal to 0 at these 2 points, the top and the bottom. So this will have a pi over 2 and a 3 pi over 2. So notice if we're looking at every single point, not just in the unit circle, so if I only wanted the points from 0 to 2 pi, then my x values, my critical points would be pi over 2 and 3 pi over 2. This would be the answer. If I wanted all the solutions, then what I'm going to do is I'm going to add 2 pi to both of them. So pi over 2 plus 2 pi k, pi over 2, 3 pi over 2 plus 2 pi k, and we'll condense it a little bit. So here k can be any integer. K is any number, any integer. Okay, so that means k can be 1, 2, 3, -1, -2, whatever you want. Now, usually this is kind of like repetitive because you have many different angles, and you can see that you can immediately get 3 pi over 2 by just adding pi. So you can easily just rewrite this a little bit as x equals pi over 2, and then just add pi k to make it a little nicer to see. Okay, so that's another way that you can do it. Since this problem didn't specify, I'm going to assume that it's all solutions. But sometimes if they just want x from 0 to 2 pi, then it would just be pi over 2 and 3 pi over 2. Okay, so now let's do another trig one. So let's say we have that one. So in this case, what we're going to do, we're going to take y prime. We're going to take the derivative of this. Derivative of 1 is 0. And then we're going to have a negative. The derivative of cosine is going to be negative sine of, we're going to leave the 2x by itself because it's just the chain rule. Then we're going to multiply it by the derivative of the inside, which is 2. So y prime is going to be a positive, and then I'm going to put the 2 in the front, sine 2x. And now what I'm going to do, I'm going to set this guy equal to 0. All right, so now let's find all of our critical points. So let's start off by dividing this by 2. So you're going to get sine of 2x is equal to 0. Now I'm going to try to find where exactly is the sine equal to 0. So let's ignore the 2x for now, just for now. So let's look at the unit circle, and where exactly are all of my angles equal to 0 for sine? And you can see that that's going to be at 0 and also at pi. So let's just assume right now that we're just looking at all the values that are from 0 to pi. I'm sorry, from 0 to 2 pi, all the critical points that are within that interval. So in this case, that means that the sine is going to be 0 at 0 and at pi. So this is equal to 0 and also at pi. Now, what is equal to 0 and pi? Well, the sine of that. And in that case, whatever that angle is, well, that's going to be whatever this inside part is, which is 2x. So in order to solve for x, you're just going to have to divide this by 2. So then x would be equal to 0 and then pi over 2. So these would be my two critical points at 0 and also at pi over 2. If I wanted to make it into every single, for every period, I would just add plus 2 pi k. Okay, so if I wanted to do all solutions, you would have 2x is equal to 0 plus pi k. Oh, sorry, 2 pi k. Oh, you can write pi k. That's actually better. 2 pi k. Or you can write pi plus 2 pi k. So when I divide this by 2, you would get x is equal to 0 plus pi k, and then pi over 2 plus pi k. Okay, and now let's do our last example. So now we have something with an exponential. So let's take the derivative of this. Notice that we have to use the product rule because there's two different functions. So f prime of x is going to be equal to the derivative of x is just 1. We leave the second one by itself. Plus, now the derivative of the second guy. The derivative of e is just e. So we're going to write the same thing again. But now what we're going to do is multiply it by the derivative of whatever's in the inside of e. And the inside of e is negative x squared. The derivative of negative x squared is negative 2x. So this whole guy is a derivative of this e part. And now we're just going to multiply it by the unaffected term, which is x. So let's clean this guy up. E to the negative x squared. Minus, you're going to have 2x squared, e to the negative x squared, and we're going to set this guy equal to 0. So how are we going to solve this? Well, the first thing that I notice is that these both of these guys have an e to the negative x squared. And then what's going to be left over when I factor that out? Well, I'm left with a 1 here because I snatched that guy. Minus, and I'm left with a 2x squared is equal to 0. So I'm going to set both of them equal to 0. And here, if you remember how to solve this, well, how can I solve this guy? Well, the opposite of taking an e is taking a natural log. So I'm going to take a natural log to both sides. And what I'm left here with is going to be e to the negative x squared and then 0. However, ln of 0 is impossible. So here we actually have no solution for that guy. There's nothing there. And also, e is always going to be positive. Okay? There's not it's something that's positive is never going to be 0. And then we just got to solve this guy. Minus 1, minus 1. Negative 2x squared is going to give me negative 1. So dividing by the negative gives me a 1. So x squared is going to give me 1/2. So when I take the square root to both sides, I'm going to add plus or minus to both of them. I'm going to get x is equal to plus or minus 1 over root 2. So these are two critical points that I have there. Now, could this be undefined? So undefined. Well, let's see. If I look at my most simplified part of the derivative, notice that I can rewrite this as 1 over e to the x squared, 1 minus 2x squared. So this guy's the only one that's giving me issue, this part. E to the x squared. So that e to the x squared cannot be equal to 0. So let's see what x values that gives me. But notice that when I apply a natural log to try to get rid of this guy, what's going to happen is that this guy still gives me a 0. So that means this is also not possible. So there's no points where this is undefined. So my only two critical points will just be those two.